Good afternoon, everyone. I'm Dr. Chue from KAIST. The title of my talk is Conductance Fluctuation and Dimensional Crossover in Hydrogenated Graphene Systems. This work was done in collaboration with Professor Hee-Ju Chang. For about last 10 years, graphene has generated tremendous interest in the scientific community. Although just graphene itself is a pretty interesting material, many people are trying to modify its electronic properties, for example by chemical modification, to use graphene in various purposes. Especially, hydrogenation has attracted much attention due to the metal-insulator transition. It was predicted that if graphene is fully hydrogenated, metallic graphene turns to an insulator, so-called graphene. And soon after that, it was confirmed by the experiments that metal-insulator transitions takes place in hydrogenated graphene. And some other strategies, such as patterned hydrogen adsorption on graphene, was also suggested. In all these cases, the origin of the metal-insulator transition is the band gap opening, and therefore we can classify them as band insulators. On the other hand, and more interestingly, the metal-insulator transition was also observed even at very low hydrogen concentrations. The origin of this transition in this case is not the band gap opening, but the localization of electronic states. When a little amount of hydrogen is randomly distributed in graphene, graphene should be treated as a disordered system with hydrogen defects. In our previous work, we have found that localized states appear at the low energy states in hydrogenated graphene. And we found that there is a strong conductance fluctuation due to the scattering of the localized states. And from the fact that the conductance decays exponentially with the sample size, it is clear that the localization is induced in hydrogenated graphene. Meanwhile, the electronic transport behavior of disordered systems has been extensively studied for over several decades. One of the most interesting phenomena is conductance fluctuation. Let me quote from an old Nature article. Surprise is that these samples exhibit large fluctuations in their electronic conductivity, which also vary from sample to sample. So for example, in these hydrogenated graphene non-ribbon samples, they have the same sample size and distorted concentration. And the only difference is the specific details of the disorder. And as can be seen in this plot, the conductance exhibits sample-to-sample fluctuations depending on the defect configuration. Therefore, for deeper understanding, their behavior must be understood in terms of the entire conductance distribution. If we focus on the localized transport regime, it is well known that the distribution is log normal in 1D systems, so that the distribution function of log G is Gaussian. And moreover, single parameter scaling theory predicts that there is a universal relation between representative parameters. So from this equation, we can see that the variance is directly related to the mean value of log G. And it is also important to note that their behavior strongly depends on the dimensionality of the system. In 2D or 3D systems, although the information is relatively poor, it is known that the distribution is deviated from log normal. And different scaling relations are applied for 2D and 3D systems. So far, most studies have been focused on 2D and 1D systems individually. And the motivation for this work came from a very simple question. What will happen when the dimensionality of the system changes from 2D to 1D? So in this work, we investigated crossover from 2D to 1D with the hydrogenated graphene system. We first studied a 1D and 2D system separately, and then we considered the dimensional transition behavior. Our calculations were performed using tight binding method. The nearest neighbor interactions between carbon-carbon and hydrogen-carbon bonds were considered. And all the parameters were fitted to a DFT band structure. And the conductance were calculated using Landauer-Bodiker formalisms with the recursive Green's functions method. As a first step, we examined the conductance behavior of 1D system. The calculated variances are plotted as a function of the mean value of log G. Here, we considered both armchair and zigzag edge structures, and we also considered various sample sizes and hydrogen concentrations to plot this data. We find that all the data points are well fitted to a single curve regardless of the details of the system. In the strongly localized regime, the results are well described by the 1D conventional relation. And in the quasi-localized regime, the results are described by the corrected equation with a slightly lowered curve. I'll skip the details about the correction scheme since we don't have much of a time, but important thing is that all the data points in the quasi-localized and strongly localized regime fits to a single curve. And this indicates that the hydrogenetic graphene nanoribbon systems are well explained by the 1D single parameter scaling theory. Next, we turn to study the two-dimensional system. In this case, we deal with L by L samples where the length and widths are same. And similar to the 1D case, the calculated variance values are drawn as a function of mean values. And again, all the data points are fitted to a single curve, regardless of the details. And a good overlap between our calculations and the approximate 2D single parameter scaling relations indicates that our results are within the 2D SPS regime. So to conclude for a moment, we can say that hydrogenetic graphene systems are well described by existing 1D and 2D theories. For better understanding, we also plot the skewness as a function of the mean value. Skewness is a measure of the asymmetry in the distribution, which is given by this equation. We can see that in 1D case, the skewness converges to 0 because of the perfect symmetry in the log normal distribution. However, in the 2D case, the skewness converges to a certain positive value, which means that the distribution is deviated from log normal. And so from this skewness curve and the variance curve, we can see that there is a clear distinction between 1D graphene nanoribbon and 2D graphene system. Now we examine the crossover behavior of conductance between 1D and 2D systems. By changing the dimensionality of the system from 2D to 1D, our goal is to find out if this kind of general transition is possible or not. Here, we think of two basic strategies to obtain the dimensional crossover. First one is reducing the width of the 2D sample, and second one is increasing the length. In the width reducing process, we start from a certain point on the 2D curve. And 4 typical points are given here. And from here, we gradually reduce the width of the sample. And during the process, the variance values immediately deviate from the 2D curve. And at a certain point, the values meet the 1D curve. And finally, the values start to follow the 1D curve. And similar evolutions are found in the skewness plot. The positive skewness values eventually converge to 0 for all the cases, so that the distribution shape evolves from a positively skewed distribution to a log normal form. And therefore, successful transition is obtained by width reducing process. On the other hand, such transition is not found in the length increasing process. Again, we start from a certain point on the 2D SPS curve, and in this case, we gradually increase the length of the sample. In contrast to the first strategy, the black transition curve does not reach the 1D curve. And in fact, it diverges from both 1D and 2D curve. And moreover, the skewness value does not rapidly converge to 0, although the sample length is very large. This means that the distribution function maintains the skewed shape. Therefore, in this case, the 1D SPS regime is not obtained. And this can be simply understood by following explanation. Since we start from the 2D graphene that is already localized, the width of the graphene is much larger than the localization length. So the W by L graphene nanoribbons, which are obtained by the increasing length of this graphene, the width is always very large as compared to the localization length. Since the width is too large to be considered to be as a 1D system, these results cannot be explained by the 1D localization theory. I'll summarize my talk. Hydrogenetic graphene systems are well explained by the 1D and 2D single parameter scaling theory. And dimensional transition from 2D to 1D is attainable by reducing the sample width. However, such transition is not possible by increasing the length. And finally, I would like to close my talk by raising some further questions that our present work cannot answer. First, what is the exact condition for the 1D and 2D single parameter scaling? And what is the crossover behavior from 3D to 2D or 3D to 1D? Thank you for your attention.